This is exactly this. Okay. So this information is basically the same as we can have from an experimental isotherm. Okay, so experimental data, molecular simulations, this is something we can compare face to face. Diffusing coefficients, there are also different ways, experimental ways to be able to get this information, a little bit more difficult. And what is very interesting is the fact that we have a detailed picture of the absorption phenomena on the molecular level. Okay, so we can really have a description of the structure and with all the molecules getting absorbed inside the porosity. And this could be very useful if we want to understand why an isotherm, for example, has different steps in the process. This is something we can predict with the simulations, and then we can really take snapshots, photos about the absorption phenomena, and we can really see how this is related to the absorption that we are seeing. Okay, so an example about these molecular simulations. Well, this is a paper that we published many years ago, 9 years ago. Okay, that was when I was working at Northwestern University with Professor Snar. And basically we said, okay, we were taking a family of materials, not only this NU100, but a family of material, and we were interested about hydrogen absorption. So we said, okay, we take the structure of the material, and then we start running molecular simulations, and we try to see if we can really predict the absorption performance. Amount absorbed of hydrogen at 77 Kelvin when we increase the pressure. This curve is the excess amount, and this curve here is the absolute amount. Okay, if you don't really know the difference between absolute and excess, don't worry. Okay, this is something important when we are working at high pressure. But basically, what is really critical here is the fact that experiments and simulations, they really match. Okay, they really work really nicely. Sometimes when we have so good simulations, we say, well, be careful. Did we did everything correct? Okay, we are not always expecting to have such beautiful overlap. But what is important is that the simulation is not a fitting of the experimental data. Okay, there is no numerical approach here about trying to do a fitting of the experimental data. We are running the simulations just with the information that we take from X-ray diffraction. Okay, we have the structure of this NE100 and different materials, and then we start running the hydrogen simulations, and we try to understand if we are able to predict this correctly. So we are validating the simulation approach. Once we have been able to do that, we can start applying this to a database of materials, and we can get something similar to what I have here represented on the right. What is this? This is 16,000 different metal organic frameworks represented in one single figure. Okay, every single point is one single structure, one single metal organic framework, one single Monte Carlo simulation. We can see the amount of hydrogen that we are absorbing, grams of hydrogen per liter of metal organic framework, as a function of the void fraction of the material, so how porous the material is. And you can see there is a huge cloud of materials, some of them with very high absorption capacity, some of them with much lower absorption capacity. But basically, this is something, okay, Monte Carlo simulations, high throughput screening, is something we can use to be able to screen databases with thousands of different materials, okay? And we can have this in a question, in a matter of days, weeks, okay? No more than 1 month, okay? All these 1,000 simulations, not more than 1 month. Typical examples, if we continue talking about hydrogen absorption, okay? In this case, at room temperature, okay? Different examples, and we can see how much hydrogen, grams per liter, we can absorb grams of hydrogen, obviously, per liter of metal organic framework, 200 bar, 500 bar, 900 bar. And what is important is that we can run this, in this case, we did this with the whole CCDC MOF subset, okay, the CSD MOF subset. So we have all the thousands of metal organic frameworks that we were exploring. And we have divided this into the different families that we were using, that we were developing before, okay? CPO 27, MOF 74 materials, couple paddle wheels, iron MOF sieves, okay, zinc oxide, so it's iron MOF series, or zirconium oxide metal organic frameworks. And at the end of the day, we find that One of the best materials is this pathgam extractor, something that was published by Professor Yagi some years ago, and it's a couple paddle wheel. Okay, by using these families, we can really identify what are the materials that we have here. Okay, we have more descriptions, and this is important because we know that couple paddle wheel extractors, for example, are going to show some problems with the stability, chemical stability. But if we focus on zirconium oxocluster metal organic frameworks, okay, they're going to be more stable. UI66 is one of the best examples. Some other materials will not be that stable, but still it's something that we can really learn. Okay, at least we have more information about all these different structures that we are running in these simulations. We can also find different information, so we can classify them into the porosity of the materials. We want to see if they are one-dimensional channel materials, two-dimensional, or three-dimensional porous network. Okay, we can really get information about how these different materials will work. And we can see that the 3D materials, okay, 3D porosity materials are generally a little bit better than, for example, the one-dimensional structures. For gas separation, tends to be many times the other way around. One-dimensional channels tends to be superior, but it depends on each application. Okay. We can also have some statistical analysis. All these points that you can see here, all these individual points are different individual metal organic frameworks, and we can classify these for all these different materials. So we have all these beautiful whisker plots analysis, where we can really see how the data is distributed around specific values, okay, for 200, 500, 900 bar. Basically, all these tools allow us to have much deeper understanding about how the different properties of these materials, okay, apply into what is the impact in the final performance of the metal organic frameworks, okay? We can also have this for the porosity. If we have one-dimensional channels, two-dimensional, or three-dimensional porous structure. What about mixtures, okay? What if we are not working with single component, and single component many times what we want is to have very high absorption capacity or maybe a very high working capacity, and I will continue talking about this in a second. But yeah, basically we can also apply this to mixers. If we take an example, one of the latest papers that is currently under review, we were focusing on the CO nitrogen separation, okay? And CO nitrogen separation, I mean, that's going to be really difficult. Boiling points are extremely similar, two very similar molecules, very challenging separation. What we are trying to have is this idea from the animation from Professor Wilmer. So being able to use a metal organic framework to separate these two gas molecules. The basic idea is that we have our material and we will have one isotherm, okay, maybe for CO, and then another isotherm for nitrogen. So we will be able to have two different absorption capacities, and we can separate these molecules based on this idea. What is going to be important? Well, the working capacity, which is described as the amount that we can absorb at high pressure and the amount we can absorb at low pressure. Okay, so the difference, which is between here and here, and also the working capacity for the other molecule, okay, between here and here. This is what I'm defining in this equation. We also want to know what is the selectivity, okay, what is the capability of the material to discriminate between the CO and nitrogen molecules, and also how easy it is to regenerate the material, okay, how much gas we can really work with, which is going to be related with the working capacity, but also with the total amount absorbed, okay? And then we can really do these studies with different processes. And this is going to be key because we need to involve not only Monte Carlo simulations, but also process simulations. If we want to work with pressure swing absorption, we need to use some ideas, but then we can also work with temperature swing absorption. Okay, we can increase the temperature or we can decrease the temperature. This is basically what I'm representing here. Okay, all these three different variables that I was including before: the working capacity, the selectivity, and because we don't want to have real 3D representations, we prefer to use colors and the size of the symbols. Okay, the size of the symbols is represented the size of the cavities, and the color is giving information about how easy it is to regenerate these different materials. We can do this for pressure swing absorption. We can do this for temperature swing absorption when we decrease the temperature, when we increase the temperature, and we will have different representations of this data. At the end of the day, what do we want to have? We want to have materials with very high working capacity and very high selectivity. We want to have materials that are in this corner. Okay, PSA, which is the most interesting process for chemical industry, for this kind of separations, that's going to be challenging. We don't have any materials in this corner, which is something we expect. If we go for some temperature swing absorption, yeah, we can find some interesting materials. This is made, all these database, these are couple paddle wheel structures, okay? And all these structures are coming from the MOF, CSD MOF subset. So all these names that we can see here are the names from the CSD. And they look very confusing, but at the end of the day, you just need to find them in the database. And this botpan, for example, is HCOS1, okay? A material we know and we are very, very familiar. So what is the key message in these slides? Basically, to choose the best material, we really need to move process simulation, okay? How can we really optimize what is the best working capacity and selectivity combination, okay? How can we really combine these two different ideas? We need to move to process simulation. And this is basically what we are describing in this paper. If you remember, at the beginning of the presentation, I was asking this idea, okay? Can we find a deterministic predictions for materials performance? And this is basically what I'm trying to answer here. And we have done this with oxygen storage, for example, very similar. And if we try to do this with individual materials, we can see thousands of different metal organic frameworks represented here. And this is something that we never happy with, okay? Because obviously you can say, well, best materials are the ones with specific heat of absorption, but also there are materials with an optimal heat absorption that do not perform very well, okay? So this is why of the key questions, why do we have these broad dispersions? And something we find is that as soon as we put some color here, then we have more descriptors, and then we can understand that we need to have specific void fraction and a specific heat of absorption to describe what a good material is. And to do this, to understand how these materials perform, we prefer not to use just static the representations, but dynamic websites where people can really play with all the data we are working, okay? And this is the example with this MOF Explorer that we have here. So you can really go to this website, and basically this is the pressure in bar, okay? This is the amount gravimetric that we absorb of oxygen, and this is the volumetric capacity for oxygen, okay? And you can see when we increase the pressure, we obviously increase the amount of gases that we are absorbing. But what is interesting is that these materials, which are represented by low void fraction, they don't grow too much. And all these purple ones, which are the ones which are highly porous, are the ones that obviously, because the porosity is higher, they are growing when we increase the pressure. This is dynamic, as I said, so one can really play with all these representations. They can really play and use the actual materials to try to find what is the best metal organic framework. Okay, so you have all the freedom to really be able to select specific structures and being able to understand what is the name of the structure we are working with. Okay, and by doing this, you can really go to the CCDC and find the original paper, and then you can do the synthesis of the material. So something that will allow you to have a lot of flexibility. And the next question, these experiments, are they real? Are they confirmed? Yeah. Okay, this is the example that we published 3 years ago. This is for nitrogen isotherm at 77 Kelvin, the simulation and the experiment. And again, these are completely different ideas. So we run the simulation, we select the MOF, and then we ask Professor Farha to prepare to synthesize this material. It was extracted from his lab. He did the experiment without seeing the simulation, okay? And then we compare the data. Perfect match. In terms of oxygen storage, this is the empty tank performance, okay? We increase the pressure, we increase the amount of oxygen we can put, volumetric. This is the best material that was published before our paper, okay? NU125 from Professor Farha as well. These are the simulations that we were having, and this is the experimental data. And you can see that we are able to match the experimental data really, really nicely. Okay, some differences at lower pressures, but at maximum capacity, we have very good prediction of the final performance. Still, the question I'm trying to answer is, can we find a deterministic prediction for this material performance? And I just want to stop here a little bit and say, okay, when we do all the experimental characterization, we always rely on these nitrogen isotomes and the BET equation calculations, okay? And we always find this question, is this a little bit ambiguous? So in particular, Professor Ruckerol, he was developing a sort of different criteria to be able to identify the BET surface area of materials correctly. But when people is using this, we always suspected that this was not doing really correctly. Even in our lab, we have a lot of differences. And the reason is that this is the nitrate isotherm for typical material H+1, okay? If you look at the semi-logarithmic representation, you can see there are different steps. And this is what really complicates the idea, okay? And this is very typical for metal organic frameworks. This is for X+1, this is for MIL 101. Yeah, a lot of different steps as well, not a continuous absorption. Something interesting is happening in these materials. And if we go to even more complicated structures, this is even more evident, okay? So basically what we did is, okay, let's collect 18 different isotherms, send this to 60 international laboratories and try to find what is the differences between the data. And what we found was quite striking. We were expecting to have some differences, but not so much, so many, so big differences. Every point you see here is the result of one of these different international labs, okay? We have materials like H+1, MOF5, where most of the groups are really clustering around specific numbers, okay? When we go more 5, yeah, we have a bunch of different labs that they have more discrepancies, okay? But most of them are really clustering around here. But then as soon as we go to more complicated structures, okay, look at this COF, you can really see the dispersion. And this material in particular, okay, this one that we have here, you can see the labs are completely all over the place, okay? And we have labs suggesting this material has 2,000 square meters per gram. Some others are suggesting they have 9,000 square meters per gram, okay? So there is something wrong here. Even if we have Ruckerol criteria to be able to understand what is a correct PET fitting, we are having some important differences here. We were creating a software to try to solve these problems, okay? And basically, the software is calculating all the different surface areas that are correct according to the Ruckerol criteria, okay? Strict Ruckerol criteria, and the representation is given here in blue, okay? You can see the scatter, there's some scattering data, but then we are suggesting also an additional criterion that suggests what is the optimal and consistent surface area for all these materials, okay? This is under review now, but basically this is kind of the output information you can really have from the software we develop. The paper is available in ChemArchive, and you can also go to GitHub and download the executables, okay? So if you are using Windows, Linux, Macs, that doesn't matter. You can use the software directly. You just put the data, and then you will be able to get your information about your structure, and you will end up with this take-home message. What is the BET area for your material? Okay, the deterministic prediction I was saying before, okay? Monte Carlo simulations is very useful, but it's not deterministic. We want to be able to jump from a list of different descriptors, what is the surface area, pore volume, pore size, density, composition, and being able to map what is going to be based on these descriptors, what is going to be the final performance. And the answer is on machine learning, okay? And this is what we are showing here. The comparison of Monte Carlo simulations with machine learning predictions, okay? The model training, in this case for oxygen, took about 3 weeks, which is basically the Monte Carlo simulations. But once we have this, then we can get the data in a question of seconds. For any new material, we just want to collect all these different descriptors, and we will be able to give you a prediction of the properties of the performance of the material in a question of seconds, okay? So this is a little bit the answer for this question, machine learning. How can we really convert Monte Carlo simulations into very quick predictions? And moving to some of the final questions, can we use these materials in industry? One of the key questions is, a pellet, but the problem, and I will jump these slides, okay? But at the end of the day, what we find is that if we try to apply pressure, most of the times we will collapse the whole porosity of the structures. So we wanted to develop something that was 100% MOF without any binders, without applying any pressure, just to have a material which is mechanically robust with high pore volume and very high density, okay? Because the volumetric capacity is key. This is something that we were able to develop a few years ago. So we have a list of different papers, and basically we are able to create what we call monolithic metal-organic framework. Sometimes they have this look, and sometimes they look completely glassy, but they are completely crystalline materials, okay? Highly porous materials, beautiful structures that we can use. And the difference is for nitrogen isotherm or gravimetric capacity. But if we jump to volumetric, you can see that the density of the monoliths, okay, is going to be much higher. So when we multiply this amount absorbed by the density, the monolithic outperforms the powder much, quite a big amount, okay, 3 to 4 times higher volumetric capacity than powders. We did this, we applied this for methane storage. That was the DOE target, very ambitious target. This is the best material that we found in the literature, again from Professor Farha. That was a powder of H+1. They apply pressure by hand and just to compact the material, the powder, and they were having this volumetric capacity with the real density of the material, okay? Not the single crystal density, but the real one. Then they started applying higher pressure. They were able to densify the material. The capacity was increasing. And if they continue increasing the pressure, yeah, they densify the powder, but they also destroy the porosity. And what we were doing was to create these monolithic structures that allow us to jump to this very high absorption capacity. Okay, we were able to reach this 263 cubic centimeters per cubic centimeter of material. And all this is now developed with one of the first spin-outs companies from my lab, okay, in material, which is basically trying to apply this monolithic synthesis to many different materials. What is the magic idea here? Okay, this is something that we published 6 years ago. Basically, we have some primary particles, and we have something that we call a wet gel. Okay, we have a gelation process. And if we do the typical drying process, fast drying, we will end up with a standard powder. But if we control the drying process, we can end up with these beautiful structures that you can see here. Okay, that would be falsified, something which is completely transparent, which means it's a very dense material, but still with a high porosity. Okay, so very interesting combination. We can really have more information about the structure of these materials, so we can go to high resolution TM. We have tried to apply a lot of different techniques to understand what is the nature of these monolithic materials. I don't want to spend too much time on this, but something important is we can apply this technology to any metal organic framework. Okay, so far we have been successful with all the MOFs that we have been working with. This is an example for the UIO 66 family of materials, and we can have materials with high microporosity and then different levels of mesoporosity. Okay, sometimes we call this hierarchical porosity, denser materials, and if we translate this to experimental performance, okay, we want to go for gravimetric absorption capacity for methane or CO2, we can see there is not much difference between these isotherms, okay? The material with higher mesoporosity performs better, is this one, okay? The material with lower mesoporosity, the denser one also behaves a little bit lower. But very interestingly, when we translate this to volumetric absorption capacity, you can see striking difference, okay? This is the empty tank. This is the dense metal organic framework, the dense monolith, okay? Basically, the density of this material is much higher than this one. This is why we translate all these results into very, very high absorption capacities, both for methane and CO2, okay? This is the comparison with H+1, and again, we have excellent absorption capacities. We can also work with hydrogen. This is something that we have under review now, and basically this will be the empty tank for 25 degrees, and these are different isotherms that we can collect at different temperatures. If we work at 77 Kelvin, this is the absorption isotherm we have for this monolithic material using a real density, okay? Not the single crystal density, but the real density of the material. We are able to reach just at 5 bar extremely high absorption capacities, and we are able to reach more than 40, more than 42 grams per liter, which is some of the Department of Energy targets for hydrogen storage. And just in the last minutes, I also want to say that we can extend this technology of monolithic materials to other materials, okay? Not on MOFs only, but also with covalent organic frameworks, okay? So this workshop is also about COFs, and these are my 2 slides about this. We can end up with these materials that we can see here is a monolithic material made of a covalent organic framework, okay? This is the typical, a typical COF. We were focusing on this. This paper is also under review, but you can find the preprint on internet if you really want. We can see all the beautiful organization of these materials with some of the layers, the bulk, some beautiful images about how are we creating this structure. And something that is interesting is the fact that in the powder, we just have the microporosity and some disorder mesoporosity here. When we have the monolithic material, we also have very, very interesting macroporosity created in this covalent organic framework. And this is also something we can characterize using SAX, small angle X-ray scattering. So we can really see you can see some Guineer areas that we can really apply to different sections of these SAX curves. And basically, we can also end up with a model, macroscopic model for this covalent organic framework monolith. Okay, this is basically going to be some macroporosity, and then we are going to have dense phase, which is going to be the covalent organic framework. And this is basically translated into nitrogen isotherm simulation. So we can have um, the powder is the gray curve. Okay, so we can see all this micro mesoporosity in reality of the material. And if we do Monte Carlo simulations, okay, we will be able to predict the powder very nicely. Okay, this is the 40% curve. But then if we want to have a simulation for this additional amount absorbed, we need to have this model coming from SAX. Okay, the idea of being able to represent with a gas lattice model of this macroporosity that we have in the monolithic material. Anyway, all the details are in this preprint. The questions that I was trying to ask at the beginning, can we find a deterministic prediction for materials performance? Well, I hope we have very quickly saw that, yeah, this is possible when we run Monte Carlo simulations with excellent databases and we apply also machine learning. Okay, so by combining all these different ideas, we will be able to have good predictions. And for the second question, can we translate these predictions to real materials and applications at scale? The answer is yes. We can scale up the synthesis of these materials. We are reaching kilogram synthesis per day kind of scale. So there is a number less of gas storage opportunities with all these materials. Okay, we want to exploit high absorption capacities of metal organic frameworks on hydrogen storage, carbon capture, but also different applications that we can find for all these materials. Okay, and this is something I always like to highlight, the fact that we have these beautiful molecular responses, what we call sometimes monolithic MOFs, is version 2.0 of metal organic frameworks. So just with this, I would like to finish, say thank you to everybody that has been participating in the research. So all this research is really done by an amazing team of postdocs and PhD students, okay, international students, mostly from many, many different countries, many from Europe, many from overseas, a lot of different collaborations, a lot of, well, thanks to different funding bodies, and all you for your attention.
Thank you very much, David, for this outstanding presentation. So I invite now people to ask a question. So it starts already in the chat. A question from Alessandra Quadrelli. So could you tell us more about the 6-parameter taxonomy you propose for MOF in your Chemical Science 2020 paper?
So, okay. So what we were trying to do here is basically try to find, with the previous criteria that we had, okay, that was very generic and was useful to identify all the metal organic frameworks that we had in the database, okay. So we had any metal and different ideas, and we were just looking for any metal organic framework. But obviously, when we were doing this, we started discovering that some of these criteria are very relevant for specific families of materials. And because we wanted to focus on this, because for some papers, for example, for some research, we wanted to focus on the existence of open metal sites. Okay, so in this case, if we have all the metal organic frameworks, we would say, well, we want to focus on maybe couple paddle wheels, or maybe we want to focus on CPO 25, 27, MOF 74 family of materials. Okay, this will allow us to select what are the structures we are looking for. So this is the criteria we use. This the taxonomy you mentioned. So this is basically how we were defining the different groups. But this is very flexible. So if you are not interested in these families of materials, but you are interested in some of the mill materials, for example, well, that's very easy. You can really go to Conquest and you can start applying all new criteria to be able to select your materials. And as I said, if you are looking for a tutorial about how to start doing this selection, more than the chemical science paper 2020, this CRISTENCOM is a very good tool to do that.
Okay, thank you, David. So another question from Salma B. I don't see the name, sorry. Could you give us more detail about the force field use and the influence to the results?
So most of the times we try to use generic force fields, okay? And if I go to something like this, we are using breathing force field for the metal organic framework, and then the typical force fields for the gases. I mean, I don't really remember now the details for the force field of hydrogen, but this is described in these papers. In this case, the simulation worked really well because the porosity is also really broad. Okay, and in this case, the interaction is really described by hydrogen-hydrogen interaction rather than the MOF hydrogen. We always assume that there is an overprediction in the interaction between the MOF atoms and the gases, but when we are dealing with these very open porosities, well, we don't see that much effect. Okay, if we really go to very low pressures, probably we will see some small differences, and we can see something like that when we go for nitrogen. Okay, you can see the pore volume is described correctly by these force fields. Okay, in this case is driven, but if we go to very low pressure, well, we can see that it is generally an overprediction, and this is generally because the interaction of the nitrogen molecule and the MOF is going to be higher in the simulation than in the real experimental case.
Okay, thank you. So question from Ben. Thank you for an interesting talk. Why are most of your performance measured based on the mass of the MOF? For many most application, unless the application requires regular transport, I don't understand why the weight of the MOF is so relevant.
Why the weight of the MOF is relevant?
Yes, because they say that except if you need some regular transport properties, it doesn't understand why the weight of the MOF is so relevant, because you base your performance measurement on the mass.
I think is I mean, I agree with you. I think it's the other way around. The key performance most of the times, okay, not always, the key performance is going to be the volumetric capacity of the materials. Not only for vehicles, okay, in vehicles you have a limited amount of volume that you can use, but also when you are having a, let's say, separation column, okay, based on absorption, if you have very low volumetric capacity, you can have hundreds of meters of column. Okay, so the amount of steel and the pressure drops and ideas, I mean, all this is going to be extremely expensive. So I would say it's the other way around, and I think I agree with you. Is the volumetric capacity what is really important? What I'm saying is that the density should be high because this is the only way that we can maximize this volumetric capacity of the materials. Okay, we need to have high surface area, high absorption capacity, like we have here in the case of the oxygen. And then we need to multiply these values, the gravimetric ones, by the density of the material. So only by having a high density material, we will be able to have a high volumetric capacity. If the material is too dense, obviously it's going to be not very porous. So this is the balance between density and surface area porosity.
Another question from Romain Dupuis. Very interesting talk. For MOF, have machine learning algorithms been able to find a structure of interest that were not found before? And then the second question is more philosophical. I know there's how good is the screen compared to the methods? And then the more broader question, in your experience, do the people see new materials as a solution to already existing societal issues or as a potential vector of growth? Whoa.
Okay, many questions. But
Yeah.
what is the first question?
The first one is have machine learning being able to find new structure that were not found before. So maybe you can start with this one.
Okay, yeah. So this is an important question. We haven't done this yet in our lab, but it's obviously a question that we are interested, and this is something we would like to develop. What we can offer with the machine learning is the fact that we run Monte Carlo simulations, okay? But I mean, our lab and many other labs, they have the expertise to run these kind of simulations. But if you're an experimentalist, you will find this a little bit more difficult. So what we want to offer is the fact that you synthesize a new MOF, your own MOF, you analyze surface area, pore volume, pore size, all these different ideas, and then you put them into the software, and then you will be able to find in 1 second what is going to be the predicted performance for your material. Okay, that's one of the easy things you can do with machine learning. But obviously, if you're able to have all this description of the landscape, what you are suggesting is true. You can really start using this machine learning to predict new materials. Okay, but this is an area we want to explore in the next few years. There is other people working on this as well. So it's a very important one.
So another question from Nathalie Stenou. Is it possible to prepare MOF monolith with a hierarchical porosity as you observe with COF monoliths?
Yeah, so the answer is yes. This is, I went very fast for with this slide, but this is basically what we see here, okay? UIOCC6, so the same metal organic framework, but 4 different synthesis conditions. In the one of these ones, the green one, we are having very little mesoporosity, okay? In the other ones, we are able to increase the mesoporosity here, here, and here. What we have seen is that for the mesoporosity that we have included, okay, this is very, very too wide porosity. And at the end of the day, it doesn't translate very well to volumetric absorption capacity. Okay, so that is the first question we had before. Is important the gravimetric or is important the volumetric? In my opinion, the volumetric is key. And in this case, the hierarchical porosity of these two materials is damaging the final performance. So we want to maximize the density, as I said, okay? But can we include additional porosity? Yes, we can.
There's a question basically about the impact of the shaping as monolith. If you see a loss of microporosity like pore blocking typically.
So yeah, sometimes yeah, we have found this, but we have also tried to solve these problems when we find them. This is some of the data we had in the supporting information for the nature materials. I mean, some of these materials have slightly lower surface area. Sometimes could be because of pore blocking, sometimes because we have some non-porous phases in the synthesis. Obviously, we try to optimize the material, and we have been able to advance on the synthesis of them. We also look at the kinetics, and this is what you can really see here. The kinetics in a powder is the red data. Okay, it's slightly faster than in the monolith, but in both systems, it's already quite fast. Okay, so equilibration time is generally pretty fast for both powders and monolithic materials.
And then a question that is, yes, typical, what about the mechanical stability of the monolith? Of course, yes. That's,
yeah, so that's also a very important question. And this is some data that we did about nano indentation. So we were measuring the mechanical properties of different materials. We have done this for HCUS1, CIF8, UIOCC6, and so on. What we have seen is that compared with the single crystal of the MOF, the monolithic materials, they have increased mechanical properties. So they are harder, and yeah, basically this is what you can really see here. If we compare this with a polycrystalline film, okay, this is generally the values we can find in the literature, and this is the data for our monolithic HCUS1. At the end of the day, we have materials with very good mechanical stability.
And then there are many questions, so I cannot ask all of them. So you will see them on the chat after if you want to reply, but it's impossible to time and constraint to ask all of them. So there's a question from Dong Fan about the training machine learning database. Which indicator are used for GCMC and how many structures are considered to control the quality of fitting?
So this is something we are developing these days. I think this slide is giving a good, what is this? It's a good summary of the different descriptors we are using. Okay, we try to focus mostly on geometrical descriptors. Okay, so textural properties like, as I said, surface area, pore volume, pore size, window size. Sometimes the density, the composition is something we can include, but it also depends. This is something we published some years ago, and in this machine learning, we needed to include also topology. Okay, that was about mechanical properties. So without the topology, we never had a very good description of the properties. Okay, the simulations, the machine learning data was everywhere. But as soon as we were able to include the topology into the machine learning predictions, then we had a very nice match between the simulation and machine learning. So it really depends on the final application. But for gas storage, that's mostly about the textural properties. And obviously, if you are dealing with something more specific with chemisorption, for example, that could be a very different area. Okay, but if you are really relying on physical absorption, yeah, these typical textural properties will be a good starting point.
I think we have to stop now. There's still 3, 4, 5 questions. You can have a look, David, but it's
okay.
Yeah, very popular.
I will continue. I can answer the questions in the chat now.
Yeah, I mean, there are plenty of students, and then yes, I understand they are just eager to ask questions.
Perfect.
So thank you very much again, David, for your fantastic presentation. And
thank you very much for the invitation.
Yes, and yes, we will send you the video later so that you can have a look.
Perfect.
So have a nice day, and we see each other maybe soon elsewhere. I don't know.
we will get out at some point.
Yeah.